by Professor Nιχογιαννόπουλος. Thank you so much, Professor Thiene.
Thank you, Makis. Now it is my personal pleasure to introduce Bill, Professor McKenna, a long-standing colleague for, 40 years, maybe 41 years, emeritus professor of UCL, and our Bill. So he will talk about 60 years of hypertrophic cardiomyopathy when genetics unlock novel therapies.
Thank you.
We are running a little bit out of time, but we rescheduled the program so that hopefully we will end up, well, not quite on time, but a little bit over.
So, Petros, thank you. Sorry, I was struggling with the machinery here. So after 600 years of eloquence, I'm bringing us back to a mere 60 years, but Padova is still a wonderful place where the English love to go. My talk is on really the actionability of genetics in cardiology, not simply for some of the new therapies, but also for some of the therapies we've had for many years. We all know this slide, and I just highlight that the HCM is a phenotype in search of a diagnosis. We tend to use it as a diagnosis, but it's actually in search, part of which involves a family history, as we've seen this morning, and genetics. Microphone that likes me more than the space here. So the essential thing is genetics as part of trying to understand the phenotype. And we have the good fortune that in 1990 the first gene was identified, and I'd highlight the text on the right, which was the last paragraph of the paper in the Cell paper, which says, here we have the beginnings of understanding the molecular mechanisms behind remodeling, behind hypertrophy. But I think if we're realistic, 30 years later, we haven't made a lot of progress. We did work out very quickly that there were other thin and thick filament mutations accounting for somewhere at the beginning 50% of disease, now 30 to 40% of disease. Understanding how these mutations cause disease has been very slow, and I think one of the nice hypotheses that came from Hugh Watkins' team in Oxford was related to the crew. And if you want to win the Olympics, the World Championships, or in the UK context, the Oxford-Cambridge boat race, you need the biggest, strongest rowers you can find. But more important is, do they row in unison? And if one is out of sync, the boat tips over. The analogy to cross-bridging with wild-type and mutant myosin was that some of these force-velocity profiles are different, they're inefficient, and they cause the disarray which we see. And this was a hypothesis very difficult to prove. There's no really good animal, there were and there still aren't great animal models for hypertrophic cardiomyopathy caused by myosin mutations. This is work, and I'm going to show 3 or 4 slides from German muscle physiologists Bernhard Brenner, Theresia Kraft, and here the first author, Kirschner. And you'll see this is, so myosin is expressed in the soleus muscle. So this is 19 at the top right, skinned single muscle fibers, and they look at it as a calcium sensitivity curve. So you see this is in the normals. You see the 3 controls gave up a chunk, and it's a serious chunk. It's not a push biopsy. It's a great big piece of muscle. And the controls were not 3 promising medical students or fellows whose names went on the paper. They were the 3 senior authors on the paper. And this was not a trivial biopsy, which we had to explain to our ethics committee and to our patients. This is the same process, the 719 mutation in beta-myosin heavy chain, and you see the activity, the calcium sensitivity curve is shifted to the right. And here you see this is an experiment in 16 muscle fibers from the biopsy, and each experiment took about a year. So this is serious methodology. This, however, is another mutation, the 736, and you see the curve is shifted to the left. And very interesting, if you look down on the lower left, at calcium concentrations where you would have expected no contraction, there is ongoing force, there's ongoing contraction. And is this the inefficient, prolonged contraction that, if you believe in obstruction, is present in hypertrophic cardiomyopathy? Or is this the impaired early relaxation, which you also see in hypertrophic cardiomyopathy, where there's an ongoing force being developed? This work has been taken up in part by James Spudich, who won a Lasker Prize, which is the prelude to a new, if you can make the clinical into clinical, you get a Nobel. He took a laser tweezer and was able to measure the force of a single myosin molecule. And if you just go to the bottom of the slide, the black dots are normal controls with force related, and the red dots are five or six different hypertrophic patients, different mutations. And one of the things that was consistent is that the hypertrophs had a higher force developed for these single myosins. This was schematized. There's a lot of industry related, but there was Myocardia, was the original company, sold to Bristol Myers. But this is the sort of schematizing. You see that HCM is actually shifted, the curve is shifted to the left. We've actually seen that it goes, you can see to the left, to the right, you can see a variety because it depends on the specific mutation, which is actually one of the main points related to the use of myosin inhibitors, which hasn't been solved. The other thing that came out of James Spudich's work is that, we think of the heart, if you're lifting weights and you're doing this, you think that your whole biceps, and probably the whole biceps is contracting. In the heart, roughly 75% of cross bridges are resting. They're not active. But in hypertrophic, there's a higher proportion are active, and in dilated, which is the schema that Bristol Myers and Myocardia have come out with, on the left, too many engaged cross bridges, myosin inhibitors. On the right, dilated, too few engaged. It's a simplification, but it's probably largely correct. Franco's going to talk about this, but there's a number of studies that have gone on related to myosin inhibitors, and this is now coming to market, and it's available. These are available to us. If you look at this slide, our understanding is largely a function of the technology. And none of us, very few of us, have been involved in the development of the technology, but we've all applied this technology. And I'd like to highlight two things. One is the development of the diagnostic criteria, ASH, and the second is related to gradient reduction. The first, 1973, Walter Henry, he's a cardiologist in Salem, Massachusetts, at the Salem General Hospital working. I'm not sure if he was at the National Institute of Health, but Chester Clark and Steve Epstein, who was the boss, were at the NIH. They wrote this paper, Asymmetric Septal Hypertrophy, the Unifying Link in Idiopathic Hypertrophic Stub Aortic Stenosis. And they wrote, this diagnosis of greater than or equal to 1.5 centimeters is the genetically determined pathognomonic feature of HCM. And we, roughly 50 years later, are still using that criteria. Now, M-mode, which could look at the thickest and thinnest segments, the basal septum, basal posterior wall, the ASH is correct in that context. But the 1.5 we've continued with, despite the fact that we know the thickness of the different parts of the ventricle varies, and we also know that body surface area size is important. So apart from concession to children, we have not made that concession in the application of these criteria to adults. Moving forward, we have the potential with artificial intelligence not just to have a single measurement as a diagnostic tool, with biomarkers, ECG, should be incorporated into a diagnosis. And I show you just a couple of references, but if you know, James Moon is a sort of a crusade. He's a colleague from London who was a magnetic resonance imaging expert, but he has been looking at diagnostic criteria, and it's very interesting how the mafia, us, resist accepting anything to do with change. And we're not very good at this. So the refereeing, this is going back 6 years now, has been very negative. The other comment that it's important to make in the context of myosin inhibitors, which are, quote, being marketed for obstruction, is this is our overview. And if you did a review, if Dr. Marin, who writes reviews beautifully, was doing one in 1980, he would have said, well, in 1965, this is a disease of obstruction. And in the early days, we had a stethoscope, we had a catheter, there's obstruction. Very quickly, Michael Criley, Celia Oakley, people who were very critical looked and said, wait a minute, this is not all obstruction. And from roughly 1970 until 2008, 2010, reviews would have said obstruction, a gradient of more than 30 millimeters of mercury, yes, seen in 20, 25, maybe 30% of patients. That's changed in the last 10 years. And now, obstruction is exercise-related obstruction counts as obstruction. And so now you're up to about 70% of patients. Of course, if you take many of us, particularly healthy younger people, will actually, at peak exercise, will get drop and afterload. You can record a Doppler gradient of more than 50. So, but what this gradient means is not, we've equated it as a community to the same as when it's at rest. It's not. And we need, as we go forward with these myosin inhibitors, we need to be better characterize these gradients in a much more standardized way, and we need to know what the exercise-related gradients actually mean. This is this is a proposal. This is going to be published in the Canadian Journal. But if you look at monogenic hypertrophic cardiomyopathy, we know the left-hand side, the sarcomere, myosin, heavy chain, C protein, troponin T are the commonest, and they probably account for somewhere between 30 and 40% of monogenic diagnosed HCM, bearing in mind that the diagnosis is not 100%. The second is the regulatory and structural genes. It was very nice, the presentations this morning on alpaca 3, but FHOD3, TRIM63, and there's several others. They probably account, but again, we're just beginning to understand these. Franco is an expert. I'm supposed to be an expert. We've seen very few alpaca 3s, and I've never seen a TRIM63. So, but we're beginning to understand that they're part of the spectrum of what we have not recognized or not been able to genotype. That's at least 10%, these regulatory structural genes. And then the syndromics, I think that the likelihood of having isolated hypertrophic cardiomyopathy that in Fabry's, Noonan, mitochondria that we don't recognize is rare. It's got to be less than 2%. Most of these patients on the syndromic have features which are recognized. So this is not a major contribution to our unrecognized or non-genetic for not finding genes for HOCM. On the right-hand side, we're in a new world of oligogenic and polygenic risk. And the oligogenic is defined by a mean allele frequency of less than 1%. And so you'll find, say, for instance, in MYBPC3, there's examples where 0.001% of the population carry that variant, but in HCM, it's 0.01%. These are likely to be disease-causing, and also polygenic, defined as allele frequency of 1 to 5%, so it's in the community. Again, to what extent, and there's papers, it's clearly the vogue, and it's what's happening up to 30%. Does this polygenic risk explains hypertrophic cardiomyopathy? So we're into an area of new classification. But I'd point out to you that at present, overall, probably less than 10% of patients worldwide get genetic testing. And even in major American referral centers, and I won't name them, but less than 20% of people who publish on obstruction and all the elements actually do gene testing. And there's many reasons. One of them is this actionable? So here you see survival curves, and this is data from the Health and Code database, and you see myosin heavy chain, C protein, and troponin T. These curves overlap. So you look at that and say, well, does it matter whether I have a troponin mutation or a myosin mutation? And the answer has been no. But if you look, and these are decent numbers. This is more than 6,000 genotype patients with a positive result. However, if you then go back and look at what we do know, and this is 1990 publication, these 4 individuals died suddenly at the ages shown that were previously asymptomatic. One of them was making tea, another was making a bed, and basically during normal daily activity. And the hearts, McGinty, if you look at the authorship, McGinty was a pathologist, a coroner's pathologist.
Yeah.
Sorry?
No, nothing.
Sorry. Was a coroner's pathologist in in England, and because he couldn't understand how these patients had died, he sent the whole heart to Mike Davis. Mike Davis was a particularly renowned and expert pathologist, and he said, these hearts, and this on the 21-year-old girl, that's her heart, 40% of her left and right ventricle show this disarray. And he wrote, but the heart weight was normal, the mass was normal, wall thickness was normal. And he said, is this some form of hypertrophic cardiomyopathy? Well, that's Alice in Wonderland. It's sort of English going around in circles. But he said, we won't know until we find the gene. We found the gene. It's the 941. Its alleles encoding the amino acid 94. But in the family, we screened the 2 boys who were normal, and then we screened the 23-year-old girl. Abnormal ECG, normal echo. So can you die suddenly with a normal echo? It's very, very, very rare. Only for me related to 92 to 95 hotspot. But was there more information than summarizing and pushing all the data on troponin into one? Yes. This looks at troponin T hotspot versus a Galician, a Spanish family with a founder effect. You see the numbers, there's several hundred. And the red is female, or there's male and female. If you're a female with a 271 troponin T mutation, your risk of dying suddenly by the age of 50 is less than 1%. If you're a male with a 92 to 95 mutation, your risk of dying suddenly is 40 to 50%. So there is actionability in knowledge of the gene. But you need to know the specific mutation. It's similar, the MVA stands for major ventricular arrhythmia, and it's very similar for myosin. This is the alpha helix in the converter region. There's differences that are actionable. So from a clinical standpoint, this is very important. And we're in an era where the myosin inhibitors and the gene therapy, which Jackie will tell us more about, we're in an era where actually knowing the gene matters beyond what the guidelines tell us, which is exclude genocopies and provide cascade screening. Actually, the genes, the knowledge of the mutation can and should be helping us with risk stratification. And again, there's major things we don't understand about the genetics in the myosin inhibitors. The companies, individual centers know the genes in their mavacamten patients and avacamten patients, but the companies have the big data sets which have not been published, but there's information there that we as a community need to get at. The other thing that's very exciting that is the gene therapy, and again, Franco will tell you, but the Danon has been a success, and MYBPC3, the first patients have been entered into what is a phase 1B study, and the efficacy study is planned. So I should stop here because I know we're over time, but thank you, and thank you, Yorgos, for the opportunity.
Thank you, Bill. That was a marvelous overview over all the 60 years of development in genetics. I remember back in the early 80s, John Goodwin mentioning that any classification is necessarily incomplete and only serves as a bridge from total ignorance to complete understanding. So how wise he was at the time. And we are still there. We are still bridging gaps. Exactly. I think probably we should, if there is no question, we should continue, Bill, with the next